Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever feel like sifting through tons of research papers for your own work is like searching for a needle in a haystack, especially when you are trying to do a deep dive into a topic? Well, today we're talking about a super cool tool that is making that search way faster and smarter. It is called ASReview. And it is like having a super helpful assistant for scanning all those research abstracts. You know, those short summaries at the beginning of research papers that tell you if the whole paper is worth reading. Screening them by hand can take ages. And honestly, it can be really tiring. That is exactly the problem this paper tackles. The main idea is that when scientists are doing big research projects called systematic reviews or meta-analyses, they need to read a lot of study summaries called abstracts to find all the relevant information. Think about trying to gather every single study ever done on how sleep affects memory. You'd have to look through thousands of abstracts. This first part, the abstract screening, is a huge time sink and can lead to all sorts of mental fumbles and fatigue. So, smart people developed a tool called ASReview. It uses something called machine learning, which is basically teaching computers to learn from data to help speed this up. It's not fully automatic though. It's like a team up between you and the computer. ASReview uses what it learns from the abstracts you've reviewed to guess which other abstracts are most likely to be important. It then shows you the ones it thinks are most relevant, so you can focus your energy there instead of reading every single one randomly. This is a big deal because it could mean finding the right studies much faster. The paper explains how ASReview works with two main scenarios. First, how to use it for screening brand new abstracts when you don't know yet which ones are relevant. And second, how to use it to check the results you get from other automatic screening methods, maybe even ones using fancy new AI like ChatGPT. Now, let's dive a bit deeper into the science behind how this works. When we do research, we often follow a process. It starts with figuring out what question we want to answer. Then we search for existing research on that topic. After that, we have to go through all the titles and abstracts to pick out the useful ones. This is the part ASReview helps with. The paper really emphasizes how time-consuming this screening step is. They even mention that screening just one abstract can take about 30 seconds, and if you have thousands of them, you are looking at potentially months of work. That is why using tools like ASReview is so exciting. They use something called active learning. Imagine you are teaching a student. You give them a few examples, they try to answer some questions, and based on how they do, you give them more targeted examples. Active learning in ASReview is similar. It starts with a few abstracts you've labeled as relevant or not relevant. The computer uses this to make a guess about the remaining abstracts. Then you review the ones it flags as most important. Give it more feedback and it gets smarter. ASReview has two main ways of working. The review mode is for actual screening where you are going through abstracts. The simulation mode is super useful for experiments. It lets you test out different ways of using ASReview, like trying out different learning algorithms or different rules for when to stop screening, all using data that is already labeled. This is how the researchers in this paper figured out the best ways to use ASReview. Within ASReview, there are different math models or algorithms that do the heavy lifting. Think of it like having different chefs in the kitchen, each with their own recipe. Some are better at recognizing certain ingredients. The paper talks about things like TF-IDF and word embeddings. Don't worry too much about the technical terms, basically. These are ways the computer figures out what words mean and how they relate to each other in the abstracts. Then there is the classifier, which is like the judge that decides if an abstract is relevant based on the computer's understanding of the words. Through science experiments, they found that a combination called LR-Arsbert really seemed to work well. It helped them find about 95% of the important studies while screening way fewer abstracts than if they had done it all by hand. That is a huge time saver. One of the trickiest parts of using these AI tools is knowing when to stop. You want to be sure you've found almost all the relevant studies, but you also don't want to keep screening forever. This is where stopping rules come in. They're like guidelines to tell you when you've screened enough. The paper talks about a few different types of stopping rules. There are data-driven ones where you stop after seeing a certain number of irrelevant abstracts in a row. Then there are time-based ones where you might stop after reviewing a certain percentage of all the abstracts. The researchers here really like combining these rules, especially with something called a key study rule, which means you keep going until you found all the really important studies you already know about. So how do you actually use this tool? The paper provides a detailed tutorial. It starts with something called pre-screening. This is like a warm-up round where you screen a small, random portion of abstracts. This helps you get a feel for the topic and estimate how many relevant abstracts there are overall. In this pre-screening phase, they recommend looking at least 100 abstracts. This helps you figure out the prevalence of relevant studies, meaning what percentage of the total abstracts are actually relevant. This prevalence number is super important for later deciding when to stop. They also say to mark any really key studies you find during this phase with notes. Next comes selecting your stopping rules. The paper gives really concrete recommendations based on the prevalence you found in prescreening. For example, if you find that 5% or fewer of the abstracts are relevant, they suggest a pretty conservative stopping strategy to make sure you don't miss anything. If more abstracts are relevant, you can afford to be a bit less strict to save time. They even suggest specific numbers like stopping after reviewing 35% of the abstracts if the prevalence is low, or stopping after seeing 7 irrelevant abstracts in a row. They also remind you to check if you found all those key studies you marked earlier. Once you've set your rules, you move on to the main AI-aided screening. Here, you switch ASReview to its smart mode. It uses the Lars algorithm we talked about and presents abstracts based on its prediction of relevance. You keep screening, making sure to very carefully label each abstract. The tool will automatically stop once your chosen stopping rules are met. In their example, this process was incredibly efficient. They found 98% of the relevant studies while only screening 39% of all the abstracts. That means they saved a ton of time by not having to look at 61% of the irrelevant ones. Now, what about using ASReview with other AI tools, like those big language models that can try to label abstracts on their own? The paper calls this the mixed approach. While these fully automatic tools are getting really good, they can sometimes make mistakes or be a bit of a black box. So, the idea is to use ASReview to double-check the results from these fully automatic systems. You'd feed the abstracts labeled by the AI into ASReview, and it helps you verify them. This pre-screening stage is about checking how good the automatic tool was. Did it miss relevant ones? Did it incorrectly flag irrelevant ones? They use some pretty cool math to figure this out, like calculating sensitivity and specificity. Think of sensitivity as how good the AI is at finding the real relevant studies, and specificity as how good it is at correctly identifying the irrelevant ones. Using this information, they can then adjust their stopping rules for the ASReview part. The paper offers different strategies for selecting stopping rules, depending on how accurate the initial automated screening was. If the automatic tool was very accurate, you can be a bit more relaxed with your ASReview stopping rules. If it wasn't so accurate, you'll want to be more careful and conservative with your ASReview rules to catch any missed relevant papers. The actual ASReview screening process in this mixed approach is similar to the first scenario, but you are feeding it already pre-labeled data. The important part is that ASReview helps you refine and verify the AI's initial classifications, ensuring you don't miss crucial information while still gaining efficiency. They also suggest extra steps you can take to make your review even more robust. This could involve using different AI models to check for agreement, or even rescreening abstracts that were initially marked as irrelevant, just to be absolutely sure. And a really big point throughout the paper is the importance of documenting everything. This makes your research transparent and reproducible, which is a cornerstone of good science. So, what is the big takeaway here, ASReview? Especially when used with these evidence-based strategies for stopping rules and model selection, can dramatically speed up the process of finding relevant research papers. It is all about working smarter, not harder. It allows researchers to get to the important findings faster without sacrificing the thoroughness needed for reliable systematic reviews. Now, for my take, this paper is a fantastic practical guide. The researchers did a great job of translating complex AI concepts into usable steps for everyday researchers. Even those who don't code, they've provided solid evidence for how to use ASReview effectively, particularly with their well-researched stopping rules. However, it is also important to remember that science is always evolving. While their simulation studies are thorough, there is always room for more real-world testing with diverse datasets to ensure these recommendations are truly generalizable across all types of research. The fact that they acknowledge this limitation is a sign of a strong scientific paper. The implications here, though, are huge. Imagine making systematic reviews faster. That means we can get evidence-based answers to pressing questions more quickly, informing everything from medical treatments to educational policies. Future research could really explore how these advanced AI models, like the LLMs, can be even more seamlessly integrated with ASReview to further boost accuracy and speed. And perhaps exploring how journals and academic communities will standardize the reporting of these AI-assisted screening methods will be the next frontier. Overall, this is a really important paper for anyone involved in research syntheses. It demystifies AI-assisted screening and empowers researchers to use these tools responsibly and effectively. What do you think about using AI to speed up research? Let me know your thoughts in the comments below. And if you found this breakdown useful, please give this video a thumbs up, subscribe to Rubin's Mind Lab for more science explained, and hit that notification bell so you don't miss our next exploration into the fascinating world of research. Thanks for watching, and I'll see you in the next one.